What specific problem does the SPA framework address in the context of instruction tuning and response generation?
The SPA framework specifically addresses the problem of generating diverse and high-quality responses from foundation models during instruction tuning. It does this by leveraging synthetic datasets and employing a systematic approach that includes computing data attribution scores, partitioning the synthetic dataset, and training multiple model adaptations. Each adaptation focuses on a distinct subset of the data, capturing unique aspects and yielding varied model behaviors, which enhances the diversity of the generated responses. The framework mitigates the diminishing returns associated with fine-tuning a single model on large synthetic datasets by allowing for specialized adaptations that maintain quality while improving response diversity. Ultimately, SPA enhances the overall user experience by providing a richer set of outputs that reflect different perspectives or styles.
Can you illustrate how the proposed SPA framework works step by step, focusing on each main component of the method?
The proposed Synthesize, Partition, then Adapt SPA framework operates through a systematic three-step process. First, it computes data attribution scores for synthetic data points using methods like the influence function, which quantifies the importance of each training point to the model's predictions. Second, the framework partitions the synthetic dataset into K subsets based on these scores, ensuring that data points within each subset have similar impacts on the model's predictions, typically using a clustering algorithm. Finally, it trains multiple foundation model adaptations on these subsets using parameter-efficient fine-tuning techniques, allowing each adaptation to focus on specific aspects of the data that yield distinct model behaviors. This structured approach enables the generation of diverse and high-quality responses by sampling from the collection of adaptations during inference.
Provide an example that demonstrates how the influence of a specific training point is calculated and affects the model's predictions in the SPA framework.
In the SPA framework, the influence of a specific training point, z, on the model's predictions is calculated using the influence function, which is defined as iz equals h underscore theta caret minus 1, nabla underscore theta lz theta. Here, Lz theta is the loss function evaluated at the training point z, and h underscore theta is the Hessian matrix of the loss function with respect to the model parameters, theta. For example, after fine-tuning the pre-trained foundation model, M, on a synthetic dataset, D, the influence scores for each synthetic data point are computed with respect to a set of test queries. This results in an influence matrix, I, that quantifies how each training point impacts the model's predictions for various test points. The training points are then partitioned based on their influence scores, ensuring that data points within each subset have similar impacts on the model's predictions, which ultimately allows the model adaptations to specialize in different aspects of the data, enhancing the diversity and quality of the generated responses.
What are the advantages of using the SPA framework compared to classical instruction tuning approaches, particularly regarding the use of synthetic data?
The SPA framework offers several advantages over classical instruction tuning approaches, particularly in its effective utilization of synthetic data. Firstly, it leverages existing synthetic datasets to train multiple model adaptations, allowing for a more efficient and cost-effective method of generating diverse responses without the need for extensive human annotated data, which is often time-consuming and expensive to collect. Secondly, by employing data attribution methods like the influence function, SPA partitions the synthetic dataset into subsets that capture unique aspects of the data, enabling the training of specialized models that yield distinct behaviors and higher diversity in outputs. Additionally, the framework utilizes parameter-efficient fine-tuning techniques, significantly reducing the computational resources required to train multiple adaptations, which is a common drawback in classical approaches that typically involve training a single model on the entire dataset. Lastly, the SPA framework demonstrates that as the volume of synthetic data increases, the utility of fine-tuning a single model diminishes, thus allowing for the effective exploitation of abundant synthetic data to enhance response diversity and quality.
Describe the experimental setup used to validate the effectiveness of the SPA framework, including datasets, metrics, and benchmarks utilized.
The experimental setup to validate the effectiveness of the SPA framework involved two main domains: code generation and natural language understanding. For code generation, the base model used was Code LLAMA7B, trained on the AUS-Instruct dataset, which contains 75,000 code-related question-answering pairs generated by GPT-3. 5 Turbo. In the natural language understanding domain, Llama 2 13B served as the base model, utilizing the Platypus dataset with approximately 25,000 question-answer pairs. The evaluation metrics included average KL divergence, which measures the diversity of generated responses, and sample diversity, which assesses the uniqueness of individual responses. The framework was tested against benchmarks such as HumanEval and MBPP for code generation tasks, and various tasks like Big Bench Hard, BBH, and MMLU for natural language understanding, ensuring a comprehensive assessment of the SPA framework's performance across different scenarios.
What limitations or challenges does the SPA framework face, particularly when dealing with large language models and synthetic data?
The SPA framework faces several limitations and challenges, particularly when applied to large language models and synthetic data. One significant challenge is the vast parameter space of foundation models, which complicates the direct application of influence functions for data attribution, making it impractical to compute the full Hessian matrix. Although recent advancements have refined the methodology, the computational cost of estimating the influence of a test query across the entire synthetic dataset remains high, as it is equivalent to calculating the gradient of the dataset. Additionally, while the framework effectively partitions synthetic data and trains multiple adaptations, the diminishing returns observed when fine-tuning on large-scale synthetic datasets suggest that simply increasing the volume of data may not yield proportional improvements in model performance. Lastly, the choice of clustering algorithms for partitioning can impact the effectiveness of the adaptations, and the framework's reliance on specific data attribution methods may limit its generalizability to other contexts or datasets.